Hey, this is Sahar, and I'm going to do a screencast of my homework really quick. Let's go. Okay, so first, here we are. We are going to Java program. Cool, we have an iterative or a tracer through the maze. We have a solver for the maze, a way of displaying the maze. We also have a way of loading the maze. That's all good. Okay, so code, go. Here's the code. There are three kinds of notation that I use inside the code: cell, point, and bit string. You'll notice that there are only three instance variables, or three variables in the maze constructor: the size across, the size down, and the bit string. A bit string looks like this. It's just the, yeah. So, cell notation counts this as a 4 by 4 maze, for example. So each of these cells, what counts. Point notation says that this is 0, 0. Cell notation would say that this is 0, 0. Whereas point notation would call this 1, 1, for example. Makes sense so far? I hope so. Okay. So blah, 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 blah. Constructor, you'll notice that the default constructor makes a full maze that looks like just all filled. Doesn't really matter. This is a helper function that, given a stringed format, chops it up into a string array, each string being the length of x across of the maze. It helps us with pre-printing. Print maze, again, given a string of a maze printed out, you'll notice that we're converting from point notation, or from cell notation to point notation here. We are looking at it row by row. Notice there's two kinds of rows. There are these kinds of rows with horizontal walls and vertical walls. In these kinds of rows with horizontal walls, you'll notice that all these count as 1, but 1 might mean a plus sign or a minus sign. This takes care of that. Otherwise, we're in a vertical row where zeros are blanks and ones are pipes, and that's very easy. So use the old replace function. We've already replaced zeros for blanks up here. That is the print function. Bit print is like print, but prints it out in ones and zeros notation. Load is very easy. That's what you do. Display is a wrapper around print maze. Find index takes cell notation, returns you index notation. Remember, cell notation is, these are cells, so this is a 4 by 4. Index notation says, where in the string are you? Okay. Okay, so this is important. Is wall is a helper function I've written that, given two cells, finds out if there's a wall between them. I dealt with this using sort of deltas. So what is the change in x and what is the change in y between point 1 and point 2? Then we find out if, so dx and dy. Unless one of dx and dy is 0 and the other one is either 1 or -1, unless that happens, we'll throw an error and call it an impossible move. If that does happen, then we have a legal move. And using index notation, if you move one to the right or left, you just do that. Moving up and down, it's a bit more complex to figure out where here is up, for example. So we do that. North NESU stands for northeast southwest. It says, given a grid, where are the legal cells around it? Legal meaning just for example, the legal cells around here are, around this cell are south and west, not north and east because of the corner. Solve, the way we solved is through an iterative function, so this is sort of a wrapper around the solver, which is the iterative function. What solve does is just really take the output of the iterative function, which is the stack of moves you need to make to find a solution. If the stack has any contents at all, it means that you found a solution, return true, otherwise return false. The cool thing about this is that the trace function is also a wrapper around the solver iterative function, just given the stack of possible moves, we print them instead of discarding them. Small helper function. This is the iterative solver, the important actual meat of the program. So the base case is if the start point you're trying to go from equals the end point, then you've solved the maze. Great. Otherwise, it's a bit more tricky. You have to care about the previous point, so you don't go back the way you came. Otherwise, you sort of filter your possible moves. So it has to be a legal position on the board, as in you can't go east from the eastmost cell. You have to make sure there are no walls between the two cells. You have to make sure that you haven't been on the cell previously. And also we have a blacklist of moves that didn't work, and we'll talk more about that later. So given all that, if one of the 4 nearby cells matches all these constraints, then we add it, otherwise we don't. We do that for northeast, southwest. Then if there are no possible moves, we've hit a dead end. We remove the top of the stack of possible solutions. We add it to our void set. I think it's a hash map or something. DQ. Otherwise, so we say avoid going the way we just came because it's a dead end. Pass on that knowledge to the iterative solver and try again. But if there is a solution, if there is a possible legal good move we haven't tried yet, do that iteratively. Cool. And then this is the main method that sort of tries out these different functions and shows you the results. Cool. Alright. And I hope that made sense.